Hello everyone, this is Surajit and you are welcome to our channel. In last lecture, we have learned how to calculate electric field for discrete point charge. First, we have learned how to calculate electric field for a single point charge. Later, we have discussed superposition principle, where we have noticed that using superposition principle, we can calculate electric field if we have more than a discrete point charge, more than or single discrete point charge, let's say two charges, three charges, four charges, or n number of discrete point charges. And at the end, we have learned how to calculate electric field. So basically, we have learned how to write electric field for linear charge distribution, for surface charge distribution, and for volume charge distribution. And so we have also understood the logic behind these definitions, where if we have let's say we have this large length over this charge is distributed. So if we want to calculate electric field, then what we can do, we can just break down this large length into elementary length, and then if we calculate the charge on the elementary length, that since this elementary length is very small, so charge on the elementary length will be applied as a point charge. So first we have written electric field at point P because of this point charge, that is charge on the elementary length, and later if we integrate over this length, that will give us actually net electric field. Same logic we have also used for surface charge distribution and also for volume charge distribution. So in this video, what we'll do, using these definitions, we'll try to calculate electric field for these cases. So let's start with the first case, where we have to calculate electric field on the axis of a charge carrying circular loop. So let me draw a circular loop here. Let's say this is a circular loop, and this circular loop is carrying a uniform linear charge density lambda. Charge density could be uniform or non-uniform. So just for simplicity, let's start with the uniform charge distribution. So that is charge per unit length is constant, charge per unit length is lambda. So now what we have to do, and one more thing, let me just define the radius of this loop, let's say r. Radius of this loop is r. So now what we have to do, we have to calculate electric field on the axis of this charge carrying circular loop. Okay. So if we consider any point on the axis, so what will be the electric field on the axis that we have to calculate? So since here charge is distributed over the length, so if we want to calculate electric field using this definition, so first what we have to consider, we have to consider elementary length. Before that, we have to consider a point on the over the region where charge is distributed, and then around this region we'll consider elementary length. And the next step, what we have to do, we have to consider we have to calculate this distance r, that is the distance of the point where we want to calculate electric field from this elementary length, and then we put the value in this integration and we'll integrate over the region where the charge is distributed. So same logic we're going to use here. So for that, what we have to do, we have to first consider a point. To consider a point, and we know electric field is actually a vector quantity. So for that, let me just consider a coordinate system. Then we can easily calculate the electric field. So let's say this is our x-axis, this is our y-axis, and this is z-axis. So in this case, axis of the circular loop is actually parallel to the z-axis, and let's say center of the circular loop is at the origin of coordinate system. So now consider a point on the circular loop, so this point, and we connect this point with the center or with the origin. So this distance will be r, and let's say this angle is phi. This angle is phi. So what will be the polar coordinate of this point? This point the polar coordinate of this point will be r phi. R phi. So now if we want to write this polar coordinate in terms of rectangular coordinate, so what will be the rectangular coordinate of this point? It will be x coordinate will be r cos phi. X coordinate will be r cos phi, and y coordinate will be r sin phi. and whatever z coordinate will be 0, because this is in the xy plane. This loop is actually on the xy plane, so z coordinate will be 0. Okay, so this is the coordinate of this point. And also we have where we have to calculate electric field on the axis. So consider another point on the axis of this loop, let's say this point, and let's just assume this is P point. And what will be the coordinate of this point? Let's say the distance of this point from the origin is z. So it is on the z axis, so x coordinate, y coordinate will be 0, and z coordinate will be z. And z coordinate is z. So then what we have to do, then we have to consider elementary length. We have to consider elementary length. So for that, what we have to do, we have to increase the phi by a small angle d phi. So we'll increase the phi by small angle d phi, then there will be a small length along the directions of phi, and that is called elementary length. So in this case, what will be this elementary length? This angle is d phi. The distance of this point from the center is r, so this length will be actually r d phi. So elementary length will be r d phi. So let me just write here dl elementary length. In this case it will be r d phi. Okay, r d phi. And then next what we have to do, we have to calculate r vector. What is r vector? R vector is the position vector of the field coordinate with the source coordinate. That means the point where we want to calculate electric field, we have to write the position vector of that point with respect to the point where we have considered elementary length. So in this case, we know the coordinate of both points. So this is the source coordinate where we have considered elementary length, and this is the field coordinate where we are interested to calculate electric field. So then we have to write the position vector of this P point with respect to the source coordinate. So let me join these 2 points. So this will be our r vector. So from this figure, what we can write, how we can write r vector here. So r vector will be, so we have to write position vector of P with respect to the source coordinate. So first we have to write the x coordinate of P, then minus we have to put the value of x coordinate of source coordinate. So so we can write like P point have x coordinate 0 and source coordinate have x coordinate minus cos phi. So it will be minus r cos phi, and then I cap, same way minus r sin phi j cap, and then field coordinate, the coordinate of field point is z coordinate of field point is z, but source coordinate is 0. So in this case we can write z minus 0, that means z into k cap. So this will be the position vector of point P with respect to the source coordinate. Now what we have to do, we have to calculate magnitude of this r vector. So what will be the magnitude of this r vector? It will be simply, you can see this is a right angle triangle, origin P and this elementary length where we have considered elementary length. So from there we can write r is equals to, or simply you can take the magnitude of this vector. So what will you will get r square plus z square, r square plus under root of r square plus z square. Okay, and then just come back here. So what we have written here, that 1 by 4 pi epsilon naught dl divided by r square into r cap. So now what we can do, we can, if we multiply with r at denominator as well as numerator, then what we'll get, r into r cap, that will give you r vector, and in denominator it will be r cube. Denominator it will be r cube. So same thing we can use here. So first we'll write the definitions of electric field at point P because of this elementary length, and then we'll integrate over the loop, and that will give us the net electric field at point P. So right here the electric field, on the axis of a charge carrying circular loop can be written as is equals to. So what we have to do, we are going to use this definition. We'll use this definition. So according to this definition, what we have to write here, first we write 1 by 4 pi epsilon naught, and then lambda dl divided by r cube into r vector. R cube into r vector. Now already we have written this dl here, and we have also this r vector, so we are just going to put this value here, and then we have to integrate over the region where the charge is distributed. So in this case, on the periphery of the circle, the charge is distributed on the periphery of the circle, so we have to integrate over the periphery of the circular loop. So just put the value of this dl and r. So what we'll get 1 by 4 pi epsilon naught, and then lambda is lambda, and dl in this case r d phi, and then we have already calculated mod of r, which is r square plus z under root of r square plus z square. So cube of this r mod of r will give us r square plus z square whole to the power 3 by 2, and then we have to put the value of this r vector. So it will be r cos phi cap minus r sin phi j cap, and then z k cap, and then we have to integrate over the periphery of this loop. So over the periphery, actually here phi is only the variable. If we consider a point on the x-axis, then phi will be 0. If we consider a point on the, if we consider elementary line on the y-axis, then it will give phi, value of the phi will be 90. So here phi is only variable. So what will be the limit of the phi for complete loop? It will be 0 to 2 pi. 0 to 2 pi. So when you integrate this term, this cos phi term over the limit 0 to 2 pi, what it will give you? It will give you 0. And same way, if you take the integration of the sin phi over the limit 0 to 2 pi, this will also give you 0. So only z component will give you actually non-zero. So for z component, from z component, what we'll get d phi is equals to integration of d phi will give you phi, and then if you put the lower limit and upper limit, what you get? We'll get 2 pi. So finally, after carried out this integration, what we'll get here? We'll get 1 by 4 pi epsilon naught lambda, and then r. From integration, we'll get 2 pi, and already we have z k cap divided by r square plus z square whole to the power 3 by 2. Whole to the power 3 by 2. So now this 2 pi r into lambda. 2 pi r, it is the total length of the periphery, and per unit length have charge lambda. So lambda into 2 pi r, that will give us total charge on the circular loop. So you can write q. So q and then z divided by 4 pi epsilon naught r square plus z square equal to the power 3 by 2 k cap. Okay, so this will be the electric field at this point. This will be the electric field at a distance z on the axis of this circular loop. If it is on the above of this loop, then it will be on the and this charge is positive, source charge is positive, and if this point is above on the loop, then it will be on upward direction, so we'll write plus k cap. If we consider a point here, then this electric field actually will be downward, so we'll write minus k cap. But magnitude on both sides will be will varies like this. It will be function of z, same function of z. Okay, so now what we have to do, once we know the uh, electric field at any point on the Z, now we are interested to calculate this electric field for some particular cases. Let's write this case one by one. First, I want to we are interested to calculate electric field at the center of this loop. What will be the electric field at the exactly at the center of this loop? So right here, case one. Case 1, electric field at the center of the loop. So at the center of the loop, Z will be 0. At the center, Z will be 0. So in this formula, if we put Z equals to 0, we'll get electric field at the center of the loop. So if we put Z equals to 0, what we'll get? We'll get actually 0. So if a circular loop carries actually uniform charge distribution, then electric field at the center will be 0. When Z equals to 0, that's mean that electric field at the center will be 0. And why it will be 0, we can simply understand from this figure. Let's say this is the circular loop and it is carrying a uniform charge distribution like this, and we are interested to calculate here electric field at here. So if we consider elemental length here and electric field, so charge on this elemental length will be like a point charge, so electric field will be along this direction. And exactly we can consider another point opposite at 180 degree with this line, that means this side. So if we consider elementary length, same amount, I mean whatever elementary length we are consider here, same length if we consider here, so charge on this length will also be same, and the electric field, magnitude of electric field at the center will also be same, but directions will be in opposite direction. So because of that, these two electric field will cancel out each other. So that's mean if we consider any point on the circular loop, we'll get another point just opposite direction, which will create the electric field at the center in opposite directions, and both the point will create a same amount of magnitude of electric field will be same. I mean both the point will create a same amount of electric field at the center, but their directions will be opposite, and because of that they will cancel out each other, and due to that reason at the center of this center of a uniform charge carrying loop, electric field will be always 0. Electric field will always 0. Okay, and then second case, case 2, let's say when Z is non-zero, but it's just greater than 0, but it is very less compared to the radius of the circular loop. That's mean we are going to consider a region like this. This is our circular loop, this is the axis of this loop, so we are going to consider a point in this region where the value of Z will be very small compared to the radius, but it's a non-zero value. It's a non-zero value. So when Z is, second case, when Z is non-zero but it is much less than R, much less than R, then what will be the electric field on this region? So for that, what we know that electric field on the axis, we have already written it, and what we have noticed that electric field will be QZ divided by 4 pi epsilon naught Z square plus R square all to the power 3/2, and if this point is above the loop, then it will be plus k cap direction. So now you see, if Z is much less than R, then let's say give you one example. Let's say Z is equals to 1 centimeter and R is equals to, let's say, 100 centimeter. 100 centimeter. So in that case, if you take square of the Z and square of the R, what will be the value of these things? I mean, we can write this Z square plus R square nearly equals to R square. Nearly equals to R square. because when you take square of this r, it will give you 10 to the power 4, and z square will be simply 1. So if you just write 10,000 and 10,001, they will be almost similar. So approximately we can write z square plus r square equals to r in this limit. So if we replace this value z square plus r square equals to nearly equals to r square, then what we'll get? We'll get a qz divided by 4 pi epsilon naught. So this will replace by r square, and we have already power 3 by 2, so r square 2 will cancel out, so we'll get r cube. R cube. And if this point above this loop, then it will be in plus k cap. It is below the loop, then it will be minus k cap. Okay. So this will be the electric field in this region when z is much less than r. So the thing you have to notice here, if we in this region, if we see the variations of electric field with z, so all these terms are constant. Q 1 by 4 pi epsilon r, these are constant. So as we shift from at the center, electric field will be 0, and then if we increase the value of z, slowly electric field will also increase the value of z. As z will increase, electric field will also increase. So electric field is proportional to the z in this region. And then consider another case, let's say case 3, where z is much greater than r. When z is much greater than r, then what we can write? We can write z square plus r square nearly equals to, so in this case r was much greater than z, that's why we have replaced this r square. Now if the conditions is reversed, like if z is much greater than r, then what we can write? This is nearly equals to z square. Nearly equals to z square. So if we put the value of this thing here, so let me again write electric field at any point on the z axis will be qz divided by 4 pi epsilon naught, and then z square plus r square whole to the power 3 by 2 into k cap. Now when z is much greater than r, then we can replace this z square plus r square is equals to z square. So when you replace this z square plus r square equals to z square, what we'll get? We'll get a qz divided by 4 pi epsilon naught into z cube. So from denominator and numerator we can cancel out z. So what we'll get? We'll get q divided by 4 pi epsilon naught into z square. 4 pi epsilon naught into z square into k cap. Okay. So when you go large distance, so this is the axis, and so when z will be much greater than r, so that's mean so at that time you can see here this charge distribution will be like as a point charge, and that is really true. You can just experience these things by yourself. You just put a circular loop at somewhere on the space, and if you travel on the axis, as you will increase the distance, you will see this loop will appears to be very small, and after certain distance you will see this will be like almost point. So that's mean the charge on the loop will also be applied as a point charge, and that's why at large distance this electric field will vary like a point charge. Okay. So if we want to draw this electric field graphically, or we want to see the variations of electric field, so let me just draw a figure here. So let's say this is the electric field. So on the y-axis put the value of electric field, and this is the z-axis. Okay. So at the center electric field will be 0. When z equals to 0, electric field 0. Now as we'll increase the value of Z, when Z is much less than R, electric field will linearly increase. This direction it will be plus Z cap, and opposite direction since it will be minus Z cap, so we have to draw in this direction. So it is plus minus. So now what we have to do, when electric Z will be much greater than R, that time what we have noticed here, that electric field will actually decrease as we increase the value of Z. So at large distance, when Z is much greater than R, then electric field actually will drop as we increase the value of Z, like this, 1 by Z square. So in between, like from 0 to at large value of Z, there is no charge. So on this line, everywhere electric field should be finite and it will be non-zero. So in that case, what we can do, we can simply just increase this one. At some point it will be maximum and then it will start dropping like this. So similarly, because of symmetry, other side also electric field will vary like same way, but since it is Z cap direction, so it will be minus Z cap direction. So we have to draw an opposite direction. That's it. Okay. So this will be the electric field variation with respect to the Z. That is the distance of the point on the axis. So now the question is where this electric field will be maximum. For what value of Z this electric field will be maximum, that we have to calculate. So for that, let's say put it in a case 3. We have case 1, case 2, case 3. Now what case 4? What we are interested to calculate electric field, maximum electric field. For what value of Z electric field will be maximum, and what will be the maximum electric field. So we can write for Emax. For Emax, what we can write, del E by del Z equals to 0. Del E by del Z equals to 0. So we know the electric field. What we have to do, we have to just take a differentiation with respect to Z. So Q divided by 4 pi epsilon naught is a constant term, and then Z divided by Z square plus R square whole to the power 3 by 2. We have to take differentiation of this term and then we'll put it 0, make it 0. So when you take differentiation, what we'll get actually 1 divided by Z square plus R square whole to the power 3 by 2, and then minus this term will give you 3 Z square divided by Z square plus R square whole to the power 5 by 2, and this is equals to 0. So if we calculate the value of Z from here, so what we get, we'll get Z square plus R square minus 3Z square is equals to 0. So finally we get Z equals to plus minus root 2 R by root 2. Okay, so that's mean these are the point where value of Z will be actually R by root 2, and at this point value of Z will be minus R by root 2. Minus R by root 2. Okay, so then what will be the value of maximum electric field? Therefore Emax, so for Emax what we have to do, we have to, in this formula we have to put Z equals to R by root 2. So when you put Z equals to R by root 2, what will get, Q divided by 4 pi epsilon naught, and then Z equals to R by root 2. So R by root 2 divided by R by root 2 square, that's mean R square divided by 2 plus r square whole to the power 3 by 2, and this will give you actually 3r square. So 3r square, and then q divided by 4 pi epsilon naught. Denominator, numerator, we have r square divided by 2, and from denominator what we'll get 3r square divided by 2 whole to the power 3 by 2. So what we can write 3 into root 3 cube divided by 2 into root 2. So when we'll simplify these things, this root 2 will can multiply with the numerator, then root 2 will cancel out. So finally what we'll get q divided by 2 will cancel out, so 6 root 3 pi epsilon naught r square, pi epsilon naught r square. So this will be the maximum electric field. Maximum electric field. So when a circular loop carries a uniform charge density and over its length, and if the total charge is q, and if the radius of the circular loop is r, then the maximum electric field on the axis will be q divided by 6 pi epsilon naught 6 root 3 pi epsilon naught r square. R square. And yeah, so this will be the maximum electric field, and which point it will be maximum at z equals to r by root 2. On the axis at the center it will be 0, and when the value of z is much less than r, in this region electric field will increase linearly, and when z will be much greater than r, at this in this region electric field will be applied as a point charge, so it will decrease with the distance 1 by z square, and then between them there will at some point electric field will be maximum, and at which point when z equals to r by root 2, at that point electric field will be maximum, and maximum value of the maximum electric field will be q divided by 6 root 3 pi epsilon naught r square. Okay, good. Now in next problem what we have to solve here, in next case we have to calculate electric field at the center of a charge carrying arc. So what we have calculate here, we have calculate electric field on the axis of a circular loop. Now in next problem what we have to solve, electric field at the center of a charge carrying arc. So arc means it's not a complete circular loop, it's a part of a circular loop. It's a part of a circular loop. So again let me draw some figure here. Yep. So let's say this is y-axis, and this is x-axis, and consider a arc which is not a complete loop but it's a part of a circular loop. So only this part. So this is the angle phi naught. So this arc part create an angle at the center, arc phi naught, and let's say radius of this arc. So it will be part of a circle. So radius of this circle is, let's say, r, capital R. Then what we have to do, we have to calculate electric field at the center. So arc means it's a part of a circle. So in this case what we have considered, that this arc part create an angle phi naught at the center, and one end of the arc part is the positive x-axis and another end at angle phi naught, and radius of this arc part is r, and this arc part is carrying, let's say, again we are considering in this case just for simplicity we are considering uniform charge density, but in examiner maybe asks a non-uniform charge distribution, so we'll calculate some problem with that also for non-uniform charge distribution. Okay, so at this moment, just consider uniform charge distribution. Okay, so if we consider uniform charge distribution, then what we have to do now, we have to calculate electric field at the center of this loop. Okay, so what we have considered, we have a arc which is carrying a linear uniform charge distribution on it, and charge per unit length is lambda. The radius of this arc part is r, and the angle that is created by this at the center of this arc part by this arc is phi naught. Okay, so now we have to calculate electric field at the center, that's mean in this case at the origin. So what will be the electric field? So again, you see the charge is distributed over the length. So if we want to calculate electric field at any point, first step what we have to do, we have to consider a point on this elementary length. So let's say this is the point, this is the point. So then what we have to do, we are around this point we have to consider a elementary length. But for that, just let me join this point with the origin. So what will be the distance of this point from the origin? It will be r, because this radius of the arc part is r, and let's say this angle is phi, this angle is phi. So what will be the polar coordinate of this point? It will be r cos r phi. And if we want to write in rectangular coordinate, then what we'll write, we'll write x equals to r cos phi and y equals to r sin phi. Y equals to r sin phi, and in this case this arc is lying on the xy plane, so z will be 0. Okay, then what we have to do, we have to consider elementary length. So in this case, if we want to consider elementary length along this arc, what we have to do, we have to increase the value of phi by a small angle d phi. So when you increase the value of phi by a small angle d phi, so you'll get a elementary length like this. So what will be the elementary length? In this case, this length, this will be r d phi. This will be r d phi. So now what we have to do, we want to calculate electric field at the center of this loop. So we have to write the position vector of this origin with respect to this point, whose coordinate is r cos phi and r sin phi. That is this vector. This will be the r vector. So in this case, we have elementary length dl is equals to r d phi, and then we have to write r vector, that is the field coordinate with respect to the source coordinate. So in this case, field coordinate is the origin and source coordinate we have considered here. So this is the source coordinate. Field coordinate is 0, 0, source coordinate is r cos phi, r sin phi. So what will be this position vector of the field coordinate with respect to source coordinate? It will be simply x coordinate of source field coordinate, that is x coordinate of origin, which is 0, minus x coordinate of source coordinate. So in this case, r cos phi. So it will give you minus r cos phi I cap, and same way for y cap also, it will give you minus r sin phi j cap. Okay, so we have r vector, and what will be the magnitude of this r vector? It will be simply r. It will be simply r. So we have linear charge distribution, we know dl vector, we know r vector. So now what we have to do, we have to write, again we'll use this definition, this definition. So right here, the electric field at the center of the charge carrying arc is equals to 1 by 4 pi epsilon naught lambda dl divided by r cube into r vector, and then we have to integrate over the length. Then put the value of lambda. So in this case, uniform, lambda is uniform, and if it is non-uniform, then it will be actually function of phi. So if it is non-uniform, then what we have to do, we have to first put the value of lambda. We'll solve some problem We'll see first if it is lambda is function of phi, then we have to put the value of lambda here. In this case, lambda is uniform, so it will be independent of phi, so we can put it outside or take it outside the integration. So lambda divided by 4 pi epsilon naught, and then put the value of dl. dl is in this case r d phi divided by r cube. So r cube will be capital R cube in this case. And what is r vector now? My r vector is minus r cos phi, r cos phi r cos phi I cap minus r sin phi j cap minus r sin phi j cap. Now since this is not a complete loop, so what we have to do when you put the value of a limit of this integration, and what will be the limit of phi? In this case we have to integrate over with respect to phi. So what will be the limit of phi? So if it is point on the x-axis, then phi will be 0, and finally we have this is the end point, and that end point and this point make an angle phi naught. So in this case we have to put a limit of phi from 0 to phi naught, 0 to phi naught, and then you have to integrate these things, integrate these things, and that will give you actually the electric field at the center of this loop, center of this arc part. Now since this is not a complete loop, so examiner may ask different type of circle arc. Like let me draw a few figure here. Examiner may ask you arc part like this. This is 1/4 of a circle, 1/4 of a circle. So what will be the electric field at the center of this arc part? Or examiner may ask you what will be the electric field for a semicircle. This is also arc. This is not a complete loop. This is also part of a loop. So if this arc part carries a uniform charge density lambda and radius of this loop, let's say capital R, it's also capital R, then what will be the electric field at the center? Or maybe examiner may ask you what will be the electric field for this type of arc. This type of. Now charge distribution may be uniform or non-uniform. That will be given in the questions. So if it is uniform, then what we have to do, you can directly put this lambda outside of integration, because it is uniform, that's mean it will not be function of phi. But if it is non-uniform, then definitely it will be function of phi. At different point value will be different. So then first what you have to do, you have to put the value of lambda. It will be some function of either sine or cos phi. So you have to put that value, and then you have to take the, you have to do the integration. If it is uniform, then you have to just take out this lambda from this integration, and remaining part you have to do the integration. Okay. So if we consider this these cases, the charge distribution is uniform, then tell me what will be the electric field for this arc, what will be the electric field of for this arc, and what will be the electric field for this arc at the center, means origin, at the center of this loop. Okay. So what we have to do, we have to simply replace this limit phi naught. For first case, we have to do limit by pi by 2. So this is the starting point, this is phi equals to 0, and this is the end point of this arc. And so this part, if we connect with origin, this will make a 90 degree with the positive x-axis. So in this case, the limit of the phi naught will be 0 to pi by 2. 0 to pi by 2. So just put this limit 0 to pi by 2 and try to calculate what will be the electric field at the center. So in this case, it will be lambda divided by 4 pi epsilon naught. And then you can see here this r square will cancel out, and 1 r you can take common here. So another r will cancel out. So what we'll get? We'll get 1 by r. So you can write r here. And then what we have to do? We have to do integration from 0 to pi by 2. And what is inside? Minus cos phi I cap minus sin phi j cap. Minus cos phi I cap minus sin phi j cap into d phi. Okay. So I'll integrate with respect to phi. This I cap j cap, it is independent of phi. So only we have to integrate cos phi and sin phi. So when you do the integration, what we'll get? After carried out the integration, if we put the limit, and then finally what we'll get? We'll get a integration of cos will be sin phi, and we have already a negative sign, so it will be minus sin phi. Upper limit is pi by 2, so it will be 1. Lower limit is 0, so it will get minus I cap. And then integration of minus sin phi will be actually cos phi. And then upper limit is pi by 2, it will be 0, and then lower limit cos 0 will be 1, but with a negative sign will be there, so we will get minus j cap. So this will be the electric field at the center of this loop. So if we have an arc part like this, it is a quarter part of circle, then electric field at the center will be this. And what will be the magnitude of this part? Magnitude will be √2 lambda magnitude of electric field at the center of a arc part, which is actually quarter part of a circle. And if it is carry a linear charge density lambda, and the radius of this arc part is r, then electric field at the center of this arc part will be lambda divided by 4 pi √2 lambda divided by 4 pi epsilon naught r. 4 pi epsilon r. This will be the magnitude. And if you want to see the directions of electric field, you see if we'll have I cap j cap, but both are negative, and their magnitude of I component, magnitude of j component is equal. So electric field will be exactly on third quadrant, and it will make an angle 45 degree with both negative x-axis and negative y-axis. So electric field will be like in this direction. Okay. So I'll recommend you just try to remember this result, because later we'll going to solve. I mean, if you remember this result, then it will be easy to solve other problem also. Using this concept, we can solve other 3 problem. Like we can solve this one, we can solve this one also. So what we have to remember, just if then let's say if we have a circular loop, I mean if we have a quarter part like this, and if it is carry a linear charge density lambda per unit length, and if this charge is positive, then the magnitude of electric field at the center of the circular loop will be actually, this angle is 90, then electric field will be in this direction. And what will be the magnitude? Magnitude will be √2 lambda divided by 4 pi epsilon naught r. 4 pi epsilon naught r. Okay. And if it is negative charge, then what will happen? See, positive charge electric field is away from the source charge, but if it is negative charge, then it will be towards the source charge, so electric field will be along this direction. Electric field will be along this direction. Okay. So both the cases, magnitude will be same, √2 lambda divided by 4 pi epsilon naught r. If it is positive charge, then electric field will be along this direction. If it is negative charge, then electric field will be in this direction. Okay. So now using this result, we can calculate electric field for this arc and also electric field for this arc. Oh, so we can see that this is a superposition of 2 quarter part of a circle. From here to here, one part, and another part is from here to here. That is another part. Another part. And what we have noticed here, for this part, electric field will be along this direction. And similarly for this part, we can write electric field will be along this direction. Electric field along this direction. And if charge density here lambda, here in this region also charge density lambda, then both the electric magnitude of electric field for this part and magnitude for electric field for this part at the center will be same. So both the electric field will be same. So finally what we can do, we can decompose this electric field. So one component will be if we decompose this field, so one component will be along this direction and another component will be along this direction. And for this one, if we decompose this, then it will be along component will be along this direction and another component will be along this direction. So these two components will cancel out each other. So we'll get electric field only downward, minus j cap. And what will be the electric field? So in this case, net electric field will be along this direction. And what will be that electric field? It will be simply cos of this angle, 2 times of cos of this electric field. That's mean cos of this electric field. So we have already written a magnitude here, root 2 lambda divided by 4 pi epsilon naught. So what we'll write here, we'll write 2 into root 2 lambda divided by 4 pi epsilon naught r into cos 45 degree. Okay, cos 45 degree. Cos 45 degree is root 2. The value of cos 45 degree is root 2. So root 2, 1 by root 2. So this root 2 will cancel out. So finally what we'll get? We'll get lambda divided by 2 pi epsilon naught r. Lambda divided by 2 pi epsilon naught r. So this will be the magnitude of the electric field at the center of a semicircle, which is carrying a uniform linear charge density lambda, and the radius of this circle is r. Same way we can also calculate electric field for this arc. Electric field for this arc. So what we can do here, we can consider this arc part actually superposition of 3 quarter part of a circle. 1 quarter part is first quadrant here to here. Second part is from here to here, and third part is from here to here. Third quadrant that here. So we know the value of electric field of each part and what will be the directions of electric field. From this definition we can calculate easily. So what we can see that this part and this part, they will create same amount of electric field at the center, and they will create electric field in opposite to each other. This part will create electric field along this direction, and this part will create electric field along this direction. So they will going to cancel out each other. So we'll get only electric field because of this part. Because of this part, and this electric field will be along this direction. And what will be the value of the magnitude of this electric field? It will be simply like this value. It is also quarter part of a circle. So if the radius of this circle, this arc is r, charge per unit length lambda. So in this case, electric field at the center, net electric field at the center will be along this direction. And what will be that electric field? Electric field will be E is equals to root 2 lambda divided by 4 pi epsilon naught r. 4 pi epsilon naught r. But main thing you have to remember that these are the result only for uniform charge distribution. Uniform charge distribution. If examiner gave you a non-uniform charge distribution, then this result will not valid. The result will be different. So for that, what you have to do? You have to do this integration. If it is function of, let's say, this part, and if it is given the lambda is lambda cos phi, lambda not cos phi, then you have to multiply here, put the value of lambda here, lambda not cos phi. So cos phi you have to multiply here, and then you have to integrate from 0 to pi by 2. In that case, you have to calculate 0 to pi. In that case, you have to calculate 0 to 3 pi by 2. 0235 by 2, that will give you result at the center for non-uniform charge distribution. But if it is uniform charge distribution, then using this result you can calculate electric field for this arc and also for this arc. Okay. So I hope that you get the idea how we can calculate electric field at the center of a charge carrying arc. Okay, then take a look on the next problem. So next problem, what we have to do, we have to calculate electric field on the axis of a charge carrying thin wire. We have to calculate electric field on the axis of a charge carrying thin wire. So let me just draw a figure like this, where let's say this is the charge carrying thin wire here to here. This, and let's say length of this wire is L. Of this wire is L. Now what you have to do, we have to calculate electric field on the axis of this wire. So let's consider a point on the axis from one end, from let's say this end. This distance is Z or Z0. Okay, Z0. What you have to do, you have to consider electric field at this point P. Electric field at this point P. So again, we have a linear charge distribution, lambda. So now what we have to do, we have to calculate electric field at this point. So how we can calculate electric field at this point? So we have continuous charge distribution and charge is distributed over the length. So we have to again use this same definitions here, this definition. So according to this definition, if we want to use this definition, then what we have to do, first we have to consider elementary length. In this case, we can consider any point. Let's say one point is here, and the distance of this point from the P, let's say Z. Distance of this point with respect to this P point is Z. Now what we have to do, we have to consider elementary length over this, around this point. So in this case, we can consider this elementary length will be dz. If we consider elementary length dz, then what will be the charge on the elementary length? Lambda into dz. For that, we have to write electric field here. So in this case, the electric field on the axis of a charge carrying thin wire is E is equals to 1 by 4 pi epsilon naught, and then what you have to do, lambda into dl. So in this case, we have considered this dl is equals to dz, and then divided. What we have to do, we have to write the position vector of P point with respect to this. So what will be the position vector of this point? If we consider that is z cap direction, so we can write simply z into z cap. So what will be the magnitude of this? It will be simply z cube, and then r vector in this case will be z cap. Z cap. And then you have to integrate. So which region we have to integrate over this region? So you can see here, at this point, the value of z will be z0. The distance of this point from this point will be z0. And then we have to integrate up to this point. So at this point, the value of z will be z0 plus L. Z0 plus L. So we can put the limit z0 to z0 plus L. Z0 plus L. So finally, what we'll get 1 by 4 pi epsilon naught. Lambda is constant, you can take it outside. And in this case, z cap will also be constant. It doesn't matter you are taking elementary length here or here. Every time electric field at this point will be along towards right, which is z cap direction. We have considered in this case z cap direction. So in this case z cap you can also take outside of the integration. So finally what we'll get 1 by z into dz, 1 by z square into dz, and that we have to integrate for the limit z naught to z naught plus L. Z cap, or you can write k cap, same, eh? Z cap. Z cap. So when you do this integration, what we'll get a lambda divided by 4 pi epsilon naught. And this integration will be minus 1 by z. That's mean what we'll get 1 by z naught minus 1 by z naught plus L. Okay, z naught plus L into z cap. So now if we simplify a little bit more, what we'll get a z naught plus L minus z naught. So we'll get lambda into L divided by 4 pi epsilon naught z naught into z naught plus L. And directions will be along plus z cap. So in this direction towards right. Okay. So if we have a thin rod like this, and if it is carry linear charge density lambda over its length per unit length, then if we want to calculate, if we calculate electric field on the axis of this thin wire at a distance z naught from its one end, let's say from this end, then what will be the value of electric field? It will be lambda L divided by 4 pi epsilon naught z naught into z plus L. And z cap in this case we have considered in this direction. So in general what you can see here, if this source charge is positive, then electric field on this side will be towards right. And if we consider a point on the axis, we can also consider one point here on the axis. So in that case, if we consider this length is z naught, then electric field will, magnitude of the electric field will remain same, but the direction in this case will be towards minus z cap. If you take this is z cap, this will be minus z cap. And it will also be reversed for if this charge density is negative, then at this point electric field will be minus z cap, and at this point electric field will be plus z cap. Magnitude will remain same, lambda L divided by 2 pi epsilon z square. Okay, good. So this is very easy. If we want to calculate electric field on the axis of a where, what we have to do, simply we have to consider elementary length, and in this case this unit vector will be always, I mean if we consider this point here, so it will be always in the same direction. So that's make actual integration is very super easy. And then finally we'll get the result lambda L divided by 2 pi epsilon naught z plus L. And if it is right side, and if the source size is positive, then it will be towards right. So in this case we have considered this is z cap direction, so that's why I've written is plus z cap. If you consider a point on the left side of this wire, then it will be minus towards left direction. And in this case, if you take this is z cap direction, so this will be minus z cap direction. And if the source charge is negative, instead of plus lambda, if it is minus lambda, then directions will be reversed. And at this point it will be minus z cap, and this point it will be plus z cap. Okay, that is it. And then take a look next problem. Now we have to calculate electric field at a perpendicular distance from a charge carrying thin wire. So again we have to calculate electric field because of a charge carrying thin wire, but in this case where we have to calculate electric field. So in previous case, like this case, we have calculated on the axis of this loop, along the length of this wire. But now what we have to where we have to calculate electric field. So let's say again we have a charge carrying thin rod like this, but in this case we have to calculate electric field at a perpendicular distance, right? Some perpendicular distance at this point. Let's say this is capital R. So at this point we have to calculate electric field. So there could be a different cases like this, length of this rod can be infinite, can be semi-infinite, and this point can be exactly on the bisector of this rod. So where we are going, what we are going to do here, we are going to write a general definitions of this electric field for this type of charge carrying thin rod, where you can easily calculate electric field if this length of this wire is infinite or semi-infinite, or if this point is the bisector. Okay, so for that, again, let me just impose some coordinate system over this charge distribution. So let's assume that the wire is lying along the z-axis. So this is the z-axis, and let's say this is the y-axis, and this is x-axis. X-axis. So charge is distributed from here to here over this length, and charge per unit length is lambda. Consider one point on the y-axis at a distance r. So what will be the coordinate of this point? On the y, this point is on the y-axis, so x coordinate will be 0, z coordinate will be 0, and only y coordinate will be r. So we can write 0 or 0. Okay. Now what we have to do, since we have a linear charge density, so first we have to consider the elementary length, where the length over where the charge is distributed. So in this region, charge is distributed, on this length, charge is distributed in this case. So we have to consider elementary length on over this length. So let's consider one point, just one point at a distance z from the origin, the distance z from the origin, and then around this point, let's consider one elementary length. Since this length is parallel to the z-axis, so what will be the elementary length on the z-axis? It will be dz. dz. So now we know elementary length. Next, what we have to do, we have to join these 2 points. Join 2 points, and we have to write the position vector of this point, let's say p point, this case p point, with respect to the source coordinate. That's mean the point where we have considered elementary length. This point have coordinate 0, 0, z, and p point has coordinate 0, r, 0. So now what we have to do, we have to write the position vector of p point with respect to this source coordinate 0, 0, z point. So what will be this position vector? So first right here, dl is in this case dz, and then position vector r is equals to, what will be r here? Position vector of point p with respect to the source point 0, 0, r, 0, 0, z point. So both the point, like x coordinate of this point 0, so x component will be 0, then y component will be r I cap, r j cap, and z component will be minus z k cap. So this is r vector, and what will be the magnitude of r vector? It will be under root of r square plus z square. R square plus z square. So once we know the dl, we know the r vector, then what we can do, we can write the electric field at point P because of this elementary length. And then if we take the integration over this length, and that will give us actually net electric field. Yeah. So right here, the electric field, at a perpendicular distance r from a charge carrying thin rod charge carrying thin wire is E is equals to 1 by 4 pi epsilon naught. So again we have linear charge distribution, so we are going to use the same definition, lambda into dl. So in this case dl is dz. Then we have to put the value of r cube. So in this case mod of r cube will be r square plus z square whole to the power p by 2, and then we put the value of r. So r in this case it will be r j cap minus z k cap. And then we have to take the integration over this length. But as I told you earlier, we are going to write a general electric field, general definitions of electric field for a at a perpendicular distance from a charge carrying thin wire. So that's mean this length of this wire can be infinite, or it could be semi-infinite, or this point may be exactly on the bisector. So for this purpose, what I am going to do here, I am just replacing this integration z in terms of another variable, let's say this angle. So if you consider this elementary length at different positions, so you can see this angle will be different. So that's mean this angle will be function of z, and let's say this angle is theta. This angle is theta. So we can replace this d theta z in terms of theta. And then we'll put the value of limit of this integration in terms of theta. What will be benefit of doing this? Then we can easily calculate electric field for infinite or semi-infinite, or if it is this point is lying on the bisector of this wire. Okay, so for that, what we are trying to do here, we are trying to replace this z by this variable theta. So for that, first we have to write some relations between z and theta. So from this figure, what we can write, see, this is the triangle, right angle triangle. So from this right angle triangle, what we can write, tan theta is equals to what we can write, z divided by r, perpendicular upon base. So now if we want to write z, what will be the value of z? Value of z will be r tan theta, and we take a derivative dz by d theta. What we'll get? We'll get r tan theta, differentiation of tan theta will be sec square theta, and then d theta we can multiply this side, so to be d theta. So dz will be r sec square theta into d theta, and value of z will be r tan theta. R tan theta. So now we can replace this dz in terms of theta. So we do that, then what we'll get? We'll get 1 by 4 pi epsilon naught lambda. Again, in this case we have considered a uniform charge density, so we can take lambda outside, and then value of dz is r sec square theta into d theta, and then have r square plus z square whole to the power 3 by 2, and here we have r j cap minus z. So z we can replace by r, so r tan theta. Okay, z we are replacing here, r tan theta. R tan theta k cap. Okay, so still what now we have to integrate over with respect to theta, but still we have a z term here. So you have to replace this z also. So to replace this z, I am doing little bit a clever way. Let's say take r common from here. can take r common here. If we take r common, then we have already one r here, so it will be r square. And then if we multiply r with the denominator and numerator, so what we'll get? We'll get lambda divided by 4 pi epsilon naught r. So when you multiply r in numerator, then what we'll get? We have already one r here, another r will take common from here, and now we'll multiply with another r, so that will give you r cube. So r cube means this length cube, and under root of r square plus z square cube means this length cube. So it's the ratio of this length, and then cube of this ratio. So this will give you actually cube of the ratio of these two length. Now what will be the ratio of these two length? R divided by under root of r square plus z square base upon hypotenuse, so that will give you cos theta. So it will give you cos cube theta. Cos cube theta. So it will give us cos cube theta, and then we have sec square theta into d theta. And if we take common r here, then what we get here inside the bracket, it will be minus j cap minus tan theta k cap. Tan theta k cap. Now what will be the product of cos theta into sec theta? That will give you 1. So from here what we can write? We can write cos square theta sec square theta is equals to 1. So we'll only cos theta. We'll get only cos theta. So finally what we can write here? We can write lambda divided by 4 pi epsilon naught r, and then we have to take integration. First term will be cos theta j cap, and if we multiply with this cos theta with tan theta, what will we get? Tan theta we can write sin theta by cos theta, so cos theta will cancel out, so we'll get sin theta k cap into d theta. Okay, so now everything, all the variables is we have written in terms of theta. So what we have to do, we have to put the limit of this theta now. So basically, if we want to calculate at this point, because of this whole length, then what you have to do, you have to integrate the from this point to this point. So that's mean you have to put the value of z from here to here. But when you take value of if you take the elementary length at this point, so if I connect this point with p, so this will be the angle corresponding the value of z here, and at the final point will be here. So if we connect this point, so this will be the value of theta associated with z. And now you can see here that this is the line. With respect to this, we are taking actually angle, so in this direction and then in this direction, so these are in opposite direction. So that's why we'll take this angle is, let's say, minus theta 2, this angle is theta 1. So that's mean if we want to calculate this integration of according to z, then we have to put the limit from here to here, and the value of theta associated with z will be minus theta by minus theta 2 plus theta 1. So what we have to do, we have to the value minus theta 1 to theta minus theta 2 to theta 1. Okay, so let me draw another figure and just a little bit. Let's say this is a charge carrying wire, and we want to calculate electric field at this point. So what will be the limit of this integration? If we put the value of theta, then what we have to do, first we have to connect to in point this wire with this point. So if you connect this one and this in point, and then you have to see what is the angle between these two lines and these two lines. So in this case we have considered this is minus theta 2 and this is theta 1. So we have to take integration. If we want to calculate at this point because of complete wire, then what you have to do, you have to put the limit of theta from minus theta 2 to theta 1. Okay. So already we have done it here. So now what we have to do, we have to carry out this integration. We have to carry out this integration. So when we will carry out this integration, what we'll get actually? When we'll carry out this integration, what we'll get? We'll get final electric field at point P is equals to lambda divided by 4 pi epsilon naught r. And then we have to integrate this term cos theta. The integration of cos theta will be sine theta, and then upper limit is theta 1, lower limit is minus theta 2. So what we'll get? You'll get sine theta 1 plus sine theta 2 into I cap. Into, sorry, not I cap, it was j cap. J cap. Okay, j cap. And then in next term we have sine theta. So integration of sine theta will be minus cos theta, and then upper limit is theta 1 and lower limit is minus theta 2. So what we'll get here? We'll get cos theta 1 minus cos theta 2 k cap. Okay, cos theta 2 k cap. Okay, so this is the general definition. This is the general definition. Now what we have to do is, mainly in exam, seminar asks for either this length will be semi-infinitely long or infinitely long, or this point, if it is finite length wire, most of the time it asks what will be the electric field on the bisector of this wire. Bisector, perpendicular bisector of this wire. So let me just write down electric field for these three cases. So case 1, right here, for infinitely long wire. For infinitely long wire, if the length of this wire is infinitely long, then what will be the electric field at point P, which is at a perpendicular distance r from the wire. So in this case, we have considered a point here. This is the r distance. And then now if this wire is infinitely long, so if we connect these two point, this two in point here, so what will be the value of this angle when this length will be infinite? So you can see as we increase the length, this angle will increase, and when this goes to infinite, it will be almost like this. So it will be theta pi by 2, and this will also be pi by 2. So for infinitely long wire, theta 1 and theta 2 both will be actually pi by 2. Theta 1 and theta 2 both will be pi by 2. So if you put value of theta 1, theta 2 pi by 2, then what we'll get? We'll get E is equals to lambda divided by 4 pi epsilon naught r. So if you put value of theta 1, theta 2 pi by 2, this term will give you 0. That means k component will be 0, and here both will be 1, so we'll get 2 j cap. So finally what we'll get lambda divided by 2 pi epsilon naught r j cap. R j cap. That's mean if we generalize this result, so in this case we have calculated electric field on the y-axis at a perpendicular distance r from an infinitely long wire, and we have noticed that the electric field will be plus j cap. So if we consider a point on the x-axis, then it will be minus a plus I cap. So it will be always perpendicular to the length of the wire. If it is plus I cap, plus charge is plus, then it will be away from the source. So at this point it will be plus j cap, at this point it will be minus plus I cap. So it will be always away from the wire and it will be perpendicular to the wire. Perpendicular to the wire. So in general, what you have to remember here, if we have a infinitely long wire, so in this case, electric field at a distance r will be lambda divided by, so if we have a, let's say like this, you have an infinitely charged carrying wire, and we want to calculate electric field at this point, that is perpendicular distance r. So magnitude of electric field at this point will be lambda divided by 2 pi epsilon naught r. And what will be direction? Directions will be, if this charge is positive, then it will be away from the source. So it will along this direction, perpendicular to the length and away from the wire. And if this charge is negative, then it will be towards the wire, like this. For negative charge, it will be towards the wire. If it is positive charge, it will be away from the wire. And magnitude will be lambda divided by 2 pi epsilon naught r. 2 pi epsilon naught r. Good. Now second case, case 2. Instead of infinitely long, if it is semi-infinite. For semi-infinitely long wire, what we can write for semi-infinitely long wire? So let me draw a figure first. If it is semi-infinite, then we can draw actually two figures. Like either we can draw, so we wanted to calculate at this point the x-axis, this is y-axis, and this is z-axis. Now on the z-axis, the wire is up to infinite. So in this case, where it starts from the origin and it goes up to infinity. Z tends to plus infinity. Okay. So if it is like this, and then if we want to calculate electric field at this point at a distance r from the wire, perpendicular distance r from the wire. So in this case, what we can do when we connect two in point with this point, so we'll get a line this. So this line will make an angle, perpendicular line 0. So in this case, theta 2 will be 0, and theta 1 will be, so other in point, if we connect other in point with this point, so when you make this length infinite, then this angle will be actually 90 degrees. So in this case, theta 1 will be 90 and theta 2 will be 0. Theta 2 will be 0. So again, if we put the value of theta 1 and theta 2 in this general expression, then we'll get the value of electric field at this point because of this semi-infinitely long wire. So if you put the value of theta equals to pi by 2, theta 1 equals to pi by 2 here, and theta 2 equals to 0, what will get? This will give you 0 and this will give you 1. So we'll get 1 j cap. And here cos theta is pi by 2. So cos pi by 2 will be 0. And minus cos theta 0, that will give you 1. So minus k cap. So in that case, we will get electric field like this. E is equals to lambda divided by 2 pi epsilon naught r. Is it 2 pi or 4 pi? 4 pi. 4 pi epsilon naught r. And then this will give you j cap minus k cap. J cap minus k cap. So for this type of situations, when we have a semi-infinite well like this, and we wanted to calculate electric field at this point. So in this case, one component of this electric field will be perpendicular to the length. You see here, one component is j cap, that's mean in this direction, and another component, if this is the plus z cap, then minus k cap will be in this direction. So one component along this direction, another component will be along this direction if the source charge is positive. Source charge is positive. And what will be the magnitude at this point? So if we calculate magnitude will be root 2 lambda divided by 4 pi epsilon naught 4 pi epsilon naught r. So that's mean for this type of situation, when we have a semi-infinitely long wire and we are interested to calculate electric field at this point, so the magnitude of electric field will be this much, root 2 lambda divided by 4 pi epsilon r. Now, if the source charge is positive, that is charge per unit length, if it is positive, then electric field at this point, magnitude of this electric field will be this much, and the directions will be, it will make, first you draw a perpendicular line to the length, and then you can draw like this way. It will make 45 degree this perpendicular line. This will be the net electric field in this case. Okay, so if we have a semi-infinitely long wire, and if we want to calculate electric field at one end point at a perpendicular distance r, then the magnitude of electric field will be lambda root 2 lambda divided by 4 pi epsilon r, and directions will be 45 degree downward with the perpendicular length. But if it is negative charge, if source charge is negative, then what will happen? Everything will remain same, magnitude will remain same, but the directions in this case will be in this direction. So this is for when charge is minus lambda, and this is for plus lambda. When charge is plus lambda, that's mean if this charge is plus lambda, per unit length charge is plus lambda, then electric field will be along this direction. And if this source charge is negative, that is charge per unit length is minus lambda, then electric field will be along this direction. Okay, so we got idea how to calculate electric field for semi-infinitely long wire. Now case 3, where we want to calculate electric field on the bisector. So case 3, electric field so if the length of the wire is finite, and the length of the wire is finite, and the point P, that's mean where we wanted to calculate electric field, we have wanted to calculate electric field at point P. Now this P point P lies on the perpendicular bisector of the wire. Okay, so let me draw again this figure. This is z-axis, this is y-axis. Want to calculate at this point. Now this point is on the bisector. That means this y-axis is actually perpendicular bisector of this length. So in both the side, from origin here to here, this length and this length, both lengths are same. If both lengths are same, then what will going to happen here? You can see that if both the lengths are same, then if we connect these two end point this point where we wanted to calculate electric field, that is P point. In this case, theta 1 and theta 2 both will be actually same. Value of theta 1 and theta 2 both will be same. And let's say total length is, let's say, 2L, where L is finite length. So in this case, if we take, this is theta 2, this is theta 1. Now what will be the magnitude of theta 1? Theta 1, theta 2, both are equals to equal, and in this case let's consider theta naught. So in this case, these two angle will be equal, and this value of this two angle is theta naught. Theta naught. So then what we have to do here, we have to put the value of, in this case, value of theta 1, theta 2 both are theta naught. So when you put value of theta 1, theta 2, theta naught, this two term will cancel out, but this term will give you 2 sine theta naught. So in this case, electric field will be E is equals to lambda divided by 4 pi epsilon naught R into 2 sine theta naught j cap. Okay, sine theta naught j cap. So this is y-axis, this is x-axis, and this is z-axis. So we have considered a point on the y-axis, and y-axis in this case cut this cut this wire to equal part. So in this case, the electric field at this point at a distance r from the on the y-axis will be this much. So in general, if I consider a wire like this is my wire, and now at a perpendicular distance, if I consider a point P, and if this point is perpendicular bisector, that's mean if this line is divided this wire into two equal part, then at a distance, at a perpendicular distance r from the wire, electric field at this point will be this much. And what is theta naught here? We connect these two lines, this angle will be the theta naught. This angle will be the theta naught, and then electric field will be always perpendicular to the length. If it is positive charge, then it will be away from the wire. If it is negative charge, then it will be towards the wire. So if we simplify this thing a little bit more, then what we'll get lambda sine theta naught divided by 2 pi epsilon naught r j cap. So if in this case we have considered a point on the y-axis, that's why it is j cap. In general, if we consider like this, let's say we have a wire like this, and we want to calculate electric field at this point, which is actually on the bisector of this wire. So in this case, electric field at this point will be lambda sine theta naught divided by 2 pi epsilon r, where theta naught is this angle, and directions will be always normal to the or perpendicular to the wire. If it is positive charge, then it will be away from the wire. If it is negative charge, then it will be towards the wire. Okay. So these are three special cases. Try to remember, or main thing, if you can understand how we'll get this electric field here, then you can simply you can put the value of theta for different cases, and then from there you can get the value of electric field. But I will request you try to remember this result with this figure, this generalized figure. If we have an infinitely long wire, and if we want to calculate electric field at a perpendicular distance from the wire, then in this case, magnitude of electric field will be lambda divided by 2 pi epsilon r, and electric field will be always normal to the wire. If it is positive charge, if source charge is positive, then it will be away from the source charge, and if it is source charge is negative, then it will be towards the wire. Then second case, if it is semi-infinitely long, then magnitude of electric field will be root 2 lambda divided by 2 pi epsilon r, and directions will be, if it is source charge, then directions will be along this direction. Source charge is positive, then directions will be in this direction. If source charge is negative, then directions will be this direction. And then finally, if it is finite length, and if we want to calculate on the bisector, so in this case electric field will be magnitude of the electric field will be this much, lambda sine theta divided by 2 pi epsilon r. And in this case also electric field will be perpendicular to the length. Again, it will be depends on nature of the source charge. If the source charge is positive, then electric field will be away from the wire. If it is negative, then it will be towards the wire. Okay. Now consider the last case for today's class, that is a electric field on the axis of a charge carrying circular disc. Okay, so let me draw a figure here. So this is a circular disc, and now this is carrying a charge like this. Yeah, charge like this. And let's say radius of this circular disc is r, capital R. And what we have to do, we have to calculate electric field on the axis of the circular disc, that is along this line. Along this line. So charge is distributed over the surface, so charge per unit area, let's say sigma. And again, just for simplicity, I'm considering here the sigma is uniform. It could be non-uniform. Then we'll see if it is, instead of uniform, it is non-uniform, what will be difference. So at this moment, just consider it as a uniform, and we want to calculate electric field on the axis of this circular disc. Okay, so again, to calculate electric field on the axis of a circular disc, what I am doing here, I'm imposing one coordinate system such a way so that the origin of the coordinate system lies at the center of this circular disc. And let's say this is x-axis, this is y-axis, and the axis of this circular disc is along z-axis. Okay, z-axis. So now what we have to do, we want to calculate electric field on the z-axis. So for that, let's consider one point on the axis of this loop, that is on the z-axis, let's say P point, and at a distance z from the origin. So coordinate of the z will be 0, 0, z. 0, 0, z. And now, since charge is distributed over the surface and it is continuous charge distribution, so what we have to do, we have to use this definition now. We have to use this definition. So if we want to use this definition, then what we have to do, first we have to consider a point on the surface where the charge is distributed. Then around this surface, around this point, we'll consider the elementary area, and then we'll calculate the distance of the point from this elementary area, and then we'll put the value here, and then at the end we have to integrate over this whole area, and that will give you the electric field at this point. So if we want to use the same definition, then what we have to do here, first we have to consider a point here. Let's say this is a point, and let's say the perpendicular distance or distance of this point from the center of this circular disc is small r, and this r makes an angle with the positive x-axis is phi. Phi. Then what will be the polar coordinate of this point? We are phi. Now if I want to write the coordinate of this point in terms of rectangular coordinate, that is, so how we can write? Can write x, y, z, and what will be the value of x in terms of r phi? It will be r cos phi. Y coordinate will be r sin phi. And since this loop is lies on the xy plane, so z coordinate will be 0. Okay. Now what we have to do, we have to consider the elementary area around this point. So what will be the elementary area? That we have already actually discussed when we discussed the 2D polar coordinate system. So we can consider elementary area here. And what will be this elementary area in this case? ds, we can write r dr d phi. R dr d phi is xy plane. So in terms of x, if we want to write this elementary in terms of xy, then what will write dx dy. So if we want to write this elementary in terms of r phi, then we can write r dr d phi. So this is the elementary area. Next, what we have to do, we have to write the position vector of p with respect to this coordinate. So let me join these 2 points first. Let's join these 2 points. Yeah. Now we have to write position vector of this p, say r vector, with respect to this point. So what will be the position vector? X coordinate is 0. So 0 minus r cos phi into I cap. So this will give you minus r cos phi I cap. And then 0 minus r sin phi. So it will give you minus r sin phi j cap. And then plus z minus 0 k cap. So z k cap. Yeah. So this will be the r, and what will be the magnitude of r? It will be simply r square plus z square. So under root of small r square plus z square. Okay. So now we know the value of ds, we know the value of r, sigma is uniform, everywhere same. So now we have to use this definition here. So again, I'm just modifying this definitions in a little bit different way. So I'm multiplying with r, numerator and denominator, and then we can write in this way, sigma ds divided by r cube. So this r will be now r square will be r cube, and r into r cap numerator give you actually r vector. That is the position vector of this point with respect to the point where we have considered elementary area. Okay. So if we use this definition here, then we can write electric field at the, so the electric field at the on the axis of a charge carrying circular disk is E is equals to 1 by 4 pi epsilon naught sigma ds divided by r cube into r vector, and we know what is the value of ds in this case. Ds is r dr d phi. What is r? We have written is r here, and what is the magnitude of r? That also we have written here. So now replace the value of all these parameters. So what we'll get? We'll get 1 by 4 pi epsilon naught surface integral sigma. Now ds is r dr d phi, and then cube of r. So r cube, this is the value of r. So what will be the value of r cube? R cube will be r into r square plus z square whole to the power 3 by 2. One more thing, just let me write in this way, that is r prime. Otherwise we'll get confused. So this distance is r, and the position vector of this point with respect to this point, let's write in terms of r prime. So r prime, so in this case we'll write in r prime. So this will be the magnitude of cube of r prime, and then r prime vector. So r prime vector will be minus r cos phi I cap minus r sin phi j cap plus z k cap. Okay. So this r prime is nothing. We just because we have taken this length r, that's why we replace this r prime. It's the same thing like as we have represent here. So r prime in this case, what is this? Is position vector of p with respect to elementary area. Why we have considered elementary area? That point is r. So we just replace this r by r prime. So if we replace this r prime, then it will be r prime cube into r prime vector. So that's we have written here. R prime vector divided by r cube, and then we have put the value of r prime and r prime vector and r prime cube and value of ds. So now what you have to do, we have to do the surface integral over the area where the charge is distributed. That means over the area of this loop, area of this disk, area of this disk. So for that, what will be the limit of r? Limit of r will be 0 to capital R, because this is the radius of circular loop. And what will be limit of phi for complete circular disk? It will be 0 to 2 pi. Okay, 0 to 2 pi. So you can see here there is no, only cos phi term is here and only sin phi term is here. So when we integrate this cos phi with respect to phi, this will give you 0 over the limit 0 to 2 pi. Also sin phi term will give you 0 the limit 0 to 2 pi. So again we'll get only z component will be the non-zero component in this case. Z component will be the non-zero component in this case. So let me write in next page. So here, so E will be finally sigma divided by sigma into, so sigma you can take outside, so sigma divided by 4 pi epsilon naught, and then we have to do the integration 0 to r, 0 to 2 pi r dr d phi, and I component will be 0, j component will be 0, so we'll get only z component non-zero, so z into k cap, okay, divided by r square plus z square whole to the power 3 by 2. So now we have to integrate this term. So this is independent of phi. So integration of phi will give us 2 pi. And then we can take this z outside. So what we'll get? We'll get 2 pi sigma z. 2 pi gets sigma z divided by 4 pi epsilon naught. And then we have to integrate this r dependent term, so r dr divided by r square plus z square whole to the power 3 by 2, and directions will be plus k cap. So what will be the integration of this value of this integration? R dr divided by r square plus z square whole to the power 3 by 2. What will be the value of this integration? It will be simply minus 1 by under root of r square plus z square. And if you are unable to do this integration, let me just give you some hint. You can take this t square is equals to r square plus z square, and then just do a partial derivative. So it will give you 2 into 2t into dt is equals to 2r dr, because r is the, in this case, variable, z is fixed, so this will give you 0. So now if you replace this whole integration in terms of t, what we'll get? You will get 2t, so 2 will cancel out here actually, so t dt divided by this is t square, r square plus z square equals 3 squares. When we put it here, so it will give actually t cube. So 1 t will cancel out, So finally what we'll get a dt divided by t square. So when you integrate this term, what you'll get minus 1 by t. So at the end, if you put the value of t again in terms of r, so what we'll get the root of r square plus z square. Under root of r square plus z square. Okay, so if you do that, so finally we'll get the value of this integration minus 1 by under root of z square plus r square. Okay, so do that. Then also simplify this term. Where we'll get here, we'll get sigma z divided by 2 pi will cancel out, so we'll get sigma by 2 epsilon naught, and this will give you minus 1 by under root of r square plus z square. Plus k cap. So now if we put the limit, then what will get sigma z divided by 2 epsilon naught. So since they have a negative sign, so either you can change the limit or put simply upper limit first, then it will be negative, and then minus of lower limit, so it will give you positive value. So it will give you, when you put r equals to 0, then it will give you 1 by z minus 1 by under root of capital R square plus z square k cap. Okay, so this will give you sigma divided by 2 epsilon naught. If we multiply this z with the bracket term, what we'll get 1 minus z divided by under root of z square plus r square. Okay. Plus k cap. So in this case, we have considered the point above the loop at this point, so it will be plus k cap. If you take a point like here at this point below the loop, then electric field will be downward because the source charge is positive, so it will always arrive from the source charge, so it will be downward direction. So in that case, what we'll write here, we'll get minus k cap. Below the point minus k cap, above the point plus k cap. And at any value of z, at a distance z from both sides, either upward or downward, both the side electric field will be sigma divided by 2 pi epsilon naught 1 minus z divided by under root of z square. Okay, so this will be the variations of electric field at a distance r. Okay, again let me just write this electric field for some special point. So finally, what we have noticed here, if we have a charge carrying circular disk like this, which carries a uniform surface charge density sigma, and then on the axis of this circular disk at any point, if we calculate at an electric field at a distance z, either on above the loop or below the loop at a distance z, then we found that this electric field will be E equals to sigma divided by 2 epsilon naught, magnitude will be 1 by z divided by under root of z square plus r square, and if it is above the place, then it will be plus k cap, so in this direction, and below the plane it will be minus k cap. So at this point, I am taking this point here, so I am writing this plus k cap. Okay. So now if I want to calculate electric field at the center, so in this case, you see charge is distributed over the length, so that's mean either we'll write the electric field on the just upper side of the loop or just below the loop. Just above the loop, just below the loop, that will be the electric field on the center. So if you put a point just above the loop, then it will be electric field will be plus k cap, and then below the loop it will be minus k cap. And what we have to do, we have to put the value of z equals to 0. Of z equals to 0, then what we'll get? So case 1, electric field at the center of the loop. So what will be that electric field? Is equals to what you have to put per center, z equals to, you have to put z equals to 0. So when you put z equals to 0, what will get? You will get sigma divided by 2 pi epsilon naught. That will be the magnitude. Now if you approaching this z equals to 0 from the top side, that's mean this point will be just above the loop. So in this case it will be plus k cap, and if you approach this z equals to 0 from bottom side, so it will be just below the loop, so it will be minus k cap. So you can write plus minus k cap. Plus minus k cap. Just above the loop it will be plus k cap, just below the loop it will be minus k cap, and magnitude will be sigma by 2 epsilon naught. Sigma by 2 epsilon naught. And then let me write case 2. Case 2, let's consider the radius of this loop is very, very large, that is infinite. Radius of this loop is infinite. So when radius is infinite, that means, and the x direction and the y direction both will be infinite. So this whole charge carrying loop, now it will behave like as a charge carrying infinite plane. It will behave like as a charge carrying infinite plane, which is carrying a uniform surface charge density sigma. Uniform surface charge density sigma. So what will be the electric field above the plane, below the plane? In this case you can see here, if it is infinitely long, then at any point on the axis electric, every point later we'll see when we discuss the concept of electric field line. Everywhere electric field line will be parallel. So in this case that electric field will be independent of z. So if it is infinite, r tends to infinite. If you put the value of here, r tends to infinite, this term will give you 0. So what we'll get? We'll get sigma divided by 2 epsilon naught. That will be the magnitude. If we consider a point above the loop, then it will be along this direction. If we consider a point below the loop, so it will be along this direction. So again we can write plus minus k cap. Plus minus k cap. And then third case, case 3. Case 3, consider a point where, let's say, z is much greater than r. We are considering a point on the axis where the value of z is much greater than r. Much greater than r. Then what will happen? Then E will be sigma by 2 epsilon naught 1 divided by z divided by under root of z square plus r square. This was the electric field at a distance z. Now we are going to impose this condition where z is much greater than r. So if z is much greater than r, so in this region what we can do, we can write this electric field in a different way. So what we can do, we can take z common from here. So if we take z common, z square common from this square root, so when you take it outside it will be 1 by, it will be z, and then denominator numerator there will be z will cancel out. So what we'll get 1 divided by under root of 1 plus r square divided by z square into k cap. Now since z is much greater than r, so this ratio r square by z square, this ratio will be less than 1. So we can actually do the binomial expansion. And if we consider only first order approximation, then what we'll get? We'll get 1 by 4 pi epsilon naught 1 minus, so first take this term into a numerator, then what we'll get? We'll get 1 plus r square divided by z square whole to the power minus half. Now if we do the binomial expansion and if we consider only first order approximation, then what we get? 1 minus 1 divided by, so if we consider only first order approximation, then this power term will multiply here. So what we'll get? We'll get minus half into r square plus z square to this k cap. Now what we'll get? We'll get to simplify this term, so this minus, this will give a minus 1 and then plus 1 by 2 r square plus z square, so minus 1 plus 1 will cancel out. So what we'll get? We'll get sigma r square divided by 4 epsilon naught z square into k cap. And then if we multiply with pi, denominator and into denominator and denominator, what we'll get? We'll get pi r square sigma divided by 4 pi epsilon naught z square into k cap. So now if sigma is uniform, then pi r square into sigma, that will give you the total charge on the disk. So we can write q divided by 4 pi epsilon naught z square into k cap. So you can see, so if you look at this charge distribution on the axis, where this point is a distance, I mean at a large distance compared to the radius of this loop, then what we'll observe that this whole charge distributions will be applied as a point charge, and it will seem like this whole charge is seated at the center of this loop. Center of this loop, and that's why actually we are getting electric field like this, q divided by 4 pi epsilon r into 4 pi epsilon naught into z square. Okay, so if we look at the look from the large distance, this whole charge distributions will be applied as a point charge and will be seated at the center of the circular loop. Center of the circular loop. Okay, so at large distance electric field will drop like 1 by z square. So now we know the variation, so we can draw electric field variation. Let me just draw electric field first for positive z value, that is above the loop. Above the loop. So in this case, electric field will be positive z cap. So now at z equals to 0, what we have seen, electric field will be sigma by 2 epsilon naught plus k cap, so this much. And then you can see here, as we will increase the value of z, what will happen? So z divided by z square, this term actually will start increase. Start increase, and because of that, we'll see this term will start actually decrease, and at a large distance we have noticed that the electric field actually it will drop 1 by z square. So this electric field variations will be like this. And on the other side, when z is negative, that is on the bottom side of the loop, and this side again variation will remain same, only directions will change. So because of that, we have to draw like this. Okay, we have to draw electric field like this. So this point, electric field will be sigma divided by 2 epsilon naught k cap. When you look at this z equals to 0 point from the left side, then it will give you minus sigma divided by, So because of this negative, because of direction only, minus k cap direction. So I can write in also this way. Sigma by 2 epsilon naught, that will be the magnitude, and directions will be in this case minus k cap. And then if we increase the value of z, magnitude of the electric field actually will decrease, and at large distance it will almost drop like 1 by z square. So this will be the electric field. And one more thing you can notice here, you see that electric field at z equals to 0 actually discontinuous. Field line will start like, if you see this point, at this point electric field will be on this direction, but bottom side electric field downward. At this point electric field will be discontinuous. Okay, so that also we can see here. At this point left side it will be minus sigma by 2 epsilon naught k cap, and on right side it will be sigma by 2 epsilon naught cap. So sometimes examiner asks what will be the amount of discontinuity. So in this case, amount of discontinuity, so you can write one line here. Electric field at the center of the charge carrying circular disk is discontinuous, and amount of discontinuity is, what will write, amount of discontinuity, right side value minus left side value. So this will give you actually sigma divided by 2 epsilon naught, and then minus sigma divided by 2 epsilon naught. So this will give you sigma by epsilon naught. Sigma by epsilon naught. Okay, and why this is discontinuous? You can see that you can just understand from a simple logic. If we have an electric point charge, like let's say Q charge, at a distance r, if we want to write electric field, what we'll write? We'll write electric field Q is equals to 4 pi epsilon naught r square into r cap. But if I want to write the electric field at the position of charge, the position where charge is situated, what will be that electric field at this point? This will go to infinite and discontinuous. So at this point, where the charge is situated, at this point we cannot define the electric field. So Coulomb's law actually does not valid at that particular point. So that's why you see later when you discuss the nuclear physics, you will see there inside the nucleus actually Coulomb's law does not work. Coulomb's law does not work. So we consider the nuclear force, short range force. So that's why actually when you consider this as disk, this have, doesn't matter, let's say this is the disk, it doesn't matter how, I mean if you consider a very small point, there will be some charge, and because of that actually at this point at the center we cannot define electric field, because charge is there, and where the charge is situated over this charge we cannot define electric field, and because of that actually this discontinuity arises here. If you want to remove this discontinuity, then what we can do, I'm giving you a homework. You calculate the electric field for a circular loop, but in this case let's say remove a circular part from around its center. Okay, so make a hole of radius r smaller around its center, or say r1, and outer radius of this annular ring, let's say r2. So now what I have did here, what I have done here, I have removed this circular cut. I have produced a circular cut inside. That's mean I have removed the charge on this portion. Now there is no charge at the center. So now if you calculate this electric field, on the axis, you will see the electric field at the center will be 0 now. It will not be discontinuous, it will be continuous. And what will be the value of it? If the surface charge density is uniform, then you will see it will be 0. It will be 0. So this is homework for you. Try to calculate electric field for this annular ring whose inner radius is r1, outer radius is r2, and it is carrying a surface charge density sigma. Then what will be the electric field on the axis of this annular disk? Exactly, you have to do the same thing whatever we have done here for a circular disk. Only thing here, we have taken the limit of r from 0 to capital R, because here charge was distributed from 0 to capital R. But in this case, we have removed the charge from this region. That is, we have produced a circular cut here. So now charge is distributed over the area from r1 to r2. So what you have to take the limit here. You have to change this limit r1 to r2. So if you change this limit and do this integration, you will get the electric field, and then you put the value after carried out this integration, put the value z equals to 0 and see whether you are getting electric field discontinuous or continuous. Discontinuous or continuous. So that is homework for you, and I have done it, so I can tell you that this will be continuous. At this point you will see electric field will be 0, but you can cross check it. And why it will be 0? Because now there is no charge at the center. So that's why now if this charge is uniformly distributed over this surface, then all this charge will create a net electric field at this point 0. But if there is a charge, then if you consider a point like this, so charge that is lies other point except this point, other point, they will create a 0 electric field here. But the charge that is situated at this point, at the center, it will create a electric field to opposite direction, and this direction and this directions. And because of that, actually this discontinuity will be appeared for this circular disk, charge carrying circular disk. As soon as you will make this cut, now there is no charge at the center, so you'll see that electric field will be continuous. Electric field will be continuous. Okay, so practice this problem again and try to remember the result, because these are some standard result. If you remember this result, then in next class we will solve a few problems based on whatever we have discussed so far. Like we have discussed electric field for single charge, electric field for more than single charge, where we have to use superposition principle, and then we have learned how to calculate continuous charge distribution for these special cases. So combine all these things, will solve at least 30 to 20 to 30 problem in next class. So, and also I will upload a practice set on the community section of my YouTube channel. So try to solve it. If unable to solve it, no need to worry. Next class we'll solve actually problem only. Okay. So thank you for watching. See you in the next video.